What if the solution to our planet's biggest challenge, it isn't just a new policy or a slightly better solar panel, but a completely different way of thinking, a completely new way of computing? That's what we're diving into today, this incredible, almost science fiction intersection of quantum computing and the fight against climate change.
I know, it sounds like pure science fiction, but this idea, the idea that we could actually tackle the climate crisis by using the fundamental, kind of bizarre rules of the universe itself, well, that's becoming more and more real every single day. The big question, of course, is how would that even work?
Okay, so when you really break it down, climate change is a data problem. It's a problem of just mind-boggling complexity. I mean, think about it for a second. You've got all these interconnected variables, everything from atmospheric chemistry to global economics, all tangled together. And to solve a problem that complex, you first have to be able to, well, compute it. And that's exactly where our current technology is really starting to hit a wall.
All right, so let's dig into that a little. Why is this such an unsolvable problem for the computers we have right now? I mean, our best supercomputers, for all their amazing power, are really struggling to keep up. Let's take an example. Say you want to design a new molecule to capture carbon right out of the air. The number of possible ways you can combine atoms is, well, it's astronomical. It's more than our best machines could ever hope to simulate. And it's the same story for optimizing a huge global energy grid in real time, or for creating a climate model that can actually tell us what the impact will be on a specific city decades from now. For problems like these, our current computers they're just running out of road.
So if our current computers just can't crack this code, what can? This is where we need a completely new kind of answer. And that's where quantum computing comes into the picture.
So, what makes a quantum computer so different? Let's try a really simple analogy. Think about a regular computer. It uses bits. You can picture them like simple light switches. They can only be on or off, a 1 or a 0. That's it. But a quantum computer? It uses something called a qubit. And a qubit is more like a dimmer switch. It can be all the way on, all the way off, or it can exist in this weird blended state of both at the exact same time. And it's that incredible ability to hold multiple possibilities at once that really unlocks their power.
Now, that dimmer switch thing, it has a cool technical name, superposition. And the spinning coin is honestly the perfect way to get your head around it. Imagine you flip a coin. While it's spinning in the air, before it lands, is it heads or tails? Well, in a way, it's kind of both, right? It's in this state of potential. That's what a qubit does with the values 0 and 1. And by doing that, it can explore a massive number of potential outcomes all at the same time.
And if you thought that was weird, it gets even stranger with its twin concept, entanglement. This is where things get really wild. It's when two qubits become linked. Their fates are literally intertwined. If you measure one, you instantly know the state of the other, no matter how far apart they are, even miles apart. It's this bizarre connection that lets quantum computers perform these incredibly complex calculations, the kind that would take a regular computer millions of years to even attempt.
Okay, so we have these really mind-bending concepts, superposition and entanglement. But how do we actually translate all of this theory into practical planet-saving action?
All right, so let's get down to it. How does this help us? Well, you can think of quantum computing as having 3 potential superpowers in the fight against climate change. First, designing brand new materials from the atom up. Second, optimizing our most complex global systems. And third, well, predicting the future with the kind of accuracy we've never seen before.
Okay, let's start with that first one, materials. Right now, a lot of materials science is, well, it's trial and error in the lab. But imagine if instead, a quantum computer could perfectly simulate molecules at the atomic level. What does that mean? It means we could literally design, from scratch, the perfect material for a new kind of battery that holds way more charge. Or we could engineer a super efficient catalyst that just pulls CO2 right out of the atmosphere. We'd be building solutions literally atom by atom.
Next up, let's talk about optimization. Our global energy grid, to be honest, it's a messy, pretty inefficient beast. A quantum computer could look at the entire system at once. I mean, everything, every power plant, every transmission line, every single home, and find the absolute most efficient way to route that energy second by second. The amount of waste and emissions we could cut would be just drastic.
Okay, I know, this all sounds absolutely incredible. Maybe a little too good to be true. And you'd be right to think that. That's why it's time for a really crucial reality check. Because the road to a quantum-powered future, it is not going to be a simple one.
Yeah, for every amazing promise, there's a really serious hurdle.
For one, qubits are extremely fragile. I mean, the slightest vibration, the tiniest change in temperature, can make them lose their special quantum state in a fraction of a second. It's a problem called decoherence. And building systems that can catch and correct these errors, it's a monumental engineering challenge. And that's not even mentioning the incredible cost and complexity of just building and maintaining these things. We have to be honest. We are still in the very, very early days of this technology.
And this really gets to the heart of it, doesn't it? Quantum computing is not a magic bullet. It's not going to just make climate change disappear. It's a tool. Now, it might be the most powerful tool we've ever even conceived of, but it's still just a tool. And it's going to require all of our ingenuity, our investment, and frankly, our political will to actually use it effectively.
So, where does all this leave us? Well, it leaves us with a new variable in the equation for our future, a variable that I think represents a whole lot of hope.
But realizing this potential, that's not something that's just going to happen in a lab somewhere. It's going to demand a massive, coordinated global effort. We're going to need scientists from all over the world collaborating. We'll need governments and private companies investing for the long haul. And we need all of us, the public, to understand both the incredible promise and the very real challenges ahead.
Because ultimately, the conversation has to shift. It's not just about what the technology can do. It's about what we will choose to do with it. The immense power of this tool puts all the responsibility right back on our shoulders. And really, that is the ultimate question, isn't it? We are standing on the brink of a true computational revolution. We're building a tool that has the power to literally reshape our world. The tool is taking shape, but the choice of what we build with it, well, that choice is ours.